In this video, I am going to speak about the second kind of closed loop configuration of the operational amplifier, and it is about a non-inverting amplifier. A non-inverting amplifier is essentially the same, almost the same as the inverting configuration, except for the fact that the places of ground as well as the input voltage changes. So previously, in the case of inverting amplifier, our input was given to the inverting side and the ground was connected to the non-inverting terminal. Now the role switch, this ground is directly connected to the inverting side and this input voltage source is connected to the non-inverting side. And in all these configurations, you can see that the feedback is given to the inverting input. So you can give the feedback to the non-inverting input or to the inverting input, but for our cases, all these feedbacks are given only to the inverting inputs, not to the non-inverting input. That is because whenever you are giving the feedback to the inverting input, the gain reduces, and that is basically because of negative feedback. And if you are going to give the feedback to the this side, it's going to be a positive feedback and it can lead to some oscillations and all. So for linear applications, we will be giving the feedback to the this side, okay, to the inverting input. So here also we are having the same kind of feedback, except for the fact that the input is now switched to the non-inverting side. And the same things hold for this also, the virtual ground condition. And as per the virtual short that we have discussed previously, these two terminals, they share almost the same voltage. So if I am connecting this V1 to the Vi input, then obviously the point V1 is having a voltage Vi. So as per the feedback system, the output voltage will be generated by the operational amplifier in such a way that the voltage at V2 is almost equal to the voltage at V1, that is V2 will be equal to Vi. So there is our start. So now we can derive the closed loop gain of this non-inverting configuration. As per our virtual short condition, our V2 will be equal to V1 and which is equal to Vi. Alright. So here you have some potential. So the potential at this point is 0. Here I have a potential V2 and this potential is V0. Similar to the previous case, I have currents flowing like this, that is II and IF. So as per the Kirchhoff's current law, at this point, and if there is no current going into the operational amplifier due to its high input impedance, then I can write II is equal to IF. So my II will be equal to I feedback, and that is represented in terms of voltages like this: 0 minus V2 divided by R1. 0 is the potential at this point and V2 is the potential at this point. So the potential difference divided by the resistance value give the current through the resistance. So that is II is represented like this, which is equal to the potential difference between the two ends of the resistance R2 divided by the resistance. So it will be V2 which is equal to V2 minus VO divided by R2. I can open these things and it will be like V2 by R1, which is equal to V2 minus VO by R2, and I can cross multiply, so I get V2 minus V2 R2 is equal to V2 R1 minus VO R1, and I will be taking out things. So V2 will be taken to one side, VO will be taken to the other side. So VO R1 comes here, V2 R1 plus V2 R2, and I can take out the V2. So V2 times R1 plus R2. So that is our VO R1. Now I take the R1 to the other side and V2 to the other side. So VO by V2 on this side on the LHS, and R1 by R1 plus R2 divided by R1 on the other side. This V2 is equal to Vi. V2 can be changed to VO by Vi, which is equal to 1 plus R2 by R1. And the ratio between the output voltage and the input voltage represented by VO by Vi is now 1 plus R2 by R1. So it's just the resistance is coming into. So here also we are having the advantage of just tuning the resistances. So if your open loop gain of the operational amplifier is much high, then we have the convenience of just tuning the ratio of the resistances to achieve any kind of gain that you require. So this equation gives us the closed loop voltage gain in the case of non-inverting amplifier. So here also you can see that it's just the ratio that matters, not the actual values of R2 and R1. The actual values of R2 and R1 will be determining the current that is flowing. But if you want to have a low current kind of a setup, then you can increase the value of R2 and R1. Keeping the ratio of R2 to R1 the same, you can increase the values of R2 and R1 so that you can reduce the current that is flowing through the circuit. And that's with the non-inverting amplifier. There is a special case for a non-inverting amplifier where you will be keeping your R2 equal to 0 and R1 equal to infinity. So that means if your R1 is infinity, there is no point in having these things. That is the ground and the R1. You can just remove this entire thing. And you can short circuit this output to the input, inverting terminal. So you remove this R2 and give a short. So it's like this. Okay. So this circuit is called a voltage follower. What it does is that as per our virtual short condition, this is having a voltage Vi at this point. As the output is connected directly to the input, then the operational amplifier will try to achieve an output voltage which is almost equal to the voltage at this point, and the voltage at this point is Vi itself. So your V1 and V2 should be same, and the operational amplifier will take care of that, and in such a way the entire voltage that is present at the output will be fed back to the input, and this point voltage will be almost the same as the voltage at this point. So you can see that the voltage, whatever be the input voltage, that voltage is reflected at the output voltage due to the this kind of a short. Okay, so the entire voltage appears here, and this voltage will be equal to this voltage due to the virtual short condition. And you might be wondering why this circuit itself is an amplifier, is called an amplifier, because it's not amplifying the voltage that is given. See, the voltage here is Vi, that Vi is present here due to that operational amplifier's action, and due to this feedback presence, it will generate an output voltage Vo which is equal to Vi. So what's the point in having an amplifier? Why do we call it as an amplifier? That is because even though the voltage is not getting amplified, buffer amplifier's output current delivering capacity, it increases enormously. That is because of the smaller output impedance, very low output impedance that the buffer amplifier is having. So it can give a lot of current to the output. Suppose if you are having a motor or some device which require a lot of current, then what you do is you cannot directly drive it from a microcontroller. So what you do is you might be having the same voltage levels but that is generated by the microcontroller, but the 5 volt pin of the microcontroller cannot be directly connected to the motor. That is because the motor demands a lot of current and the microcontroller is not able to give that much amount of current. So what you need to do is you need to protect the microcontroller pins, as well as you need to deliver the information from the microcontroller to the motor, that is to run. So what you do is you put this kind of a circuit, and instead of this Vi, you will be connecting it to the microcontroller's output pin. So that microcontroller's output pin will be generating plus 5 volt, and the plus 5 volt will be here also, and that plus 5 volt appearing here can also drive the motor because of the high current delivering capacity of the operational amplifier. So thereby you have a kind of an impedance matching here, and it can give a lot of current. So this is the advantage of voltage follower circuit. So the points to take from this is, in the previous case we had two resistances R2 and R1. We put R2 equal to 0 ohms and R1 equal to infinity. So this will give you a circuit like this, and this circuit is a high current delivering circuit called voltage follower or buffer amplifier, where the voltages will be the same, the input and output voltage will be the same, and the output will be having a high current capacity. It can handle high currents, or it can give high currents to the subsequent devices. And the voltage gain in this case can be found out using this equation, where you can substitute the values for R2 and R1. And when you substitute the values for R2 I have said it is 0 ohms. So when I substitute, the voltage gain will be equal to 1 plus 0 by infinity, which is equal to 1. So your gain is always 1, but that is just the voltage gain. Current delivering capacity of the system is much higher. So that is the advantage of this special case of non-inverting configuration. So with this we can wind up the discussions on non-inverting closed loop configuration, and we can see another closed loop configuration in the next class. Thank you all.